Good morning. Today's lecture will continue on Karnaugh maps. So for 4 variables Karnaugh maps, the first step you need to determine the minterms. So the minterms will give you the location of ones. In case if you have the max terms, you can convert the max terms to minterms, then find or determine the location of ones. So when we draw the Karnaugh maps shown here, so we see that the location of ones will be at 0, 1, 2, 4, 6, 8, 9, 12, 13, and 14. So we need to determine or to find the minimum, call it minimum realization. So how we can find it, let me make sure we have 0, 1, 2, 4, 5, I forget the 5, 6, 8, 9, 12, and 13. Okay. Now we need to group. Can we group 16? No way. Can we group 8s? Yes, we can group these 8s. Now, can we group, how about we have 3 remainings? So these 3, we cannot group 3, we need to group 4. Is there a way to group 4 using these 3, remaining 3? There is a way by, we can group these 2 with these 2, so we have 4. Then we have the last one. How can we group it? We can group it as alone, or we can group it with this one and this one as 2. But our target is to group it with the largest possible, even though if there is some overlap. So what's the largest number possible to do it? Which is, we can group this with this. Because our target is there a way to group this one with 8s? No. The only way to group it with 4. Okay? So how to write the simplification? To write the simplification for the first one here, this is with the area, since it has 8s, which means it should include only one variable. So it's not, of course, it's not with z, because here is z, there is z bar. This is not with z, this is not with w, this is not with x. So look at, here is the y location, therefore this is the location of y bar. So as a result, this will be y bar. How about in pink? How about this? In pink, include 4 blocks. 4 blocks associated with 2 variables. Therefore, this is location. Let's look at the variable w. The variable w is located here. Here is w, not so. It should be w bar, the first symbol. Let's look at the symbol x. Look at the symbol x. So where is x, which is located here? So half of it with x, half of it with not. So this is not x. Look at the other variable, which is y. Variable y is located on here. So this is associated with y, this is associated with y bar. Therefore, the variable y is not included. Will not be a good option. Then the last one, which is z. This is the location of z. This is the location of z bar. Therefore, it should be in z bar area. So y bar, z bar area. Now, the last block, which is written here. This is, for this block, look at the variable w. The variable w, this is w bar, so of course this is not w. Look at the variable x. It's within the x area. Then okay, that's fine. Let's use x. Look at the other variable, which is y. This is in y. This is in y bar. Then of course this is not y. Then the last one, which is z, it will be within z bar area. So x z bar. As a result, f will be y bar plus w bar z bar plus x z bar. Okay? So now, are you familiar, or do you understand how to use to make the simplification? Okay, that's great. Let's go to another example, the other one. Simplify the following Boolean function. Okay, we have a bar b bar c bar plus a bar c bar d bar plus a bar b c d plus a b bar c bar. The first step, find the minterms. Now, this expression is not in the general formula because this is 4 variables, or it should be 4 variables Carnot map. So in 4 variables, you will see the first term includes 3, the second term 3, third term 4, fourth term 3. So we need to convert each term to be in 4 variables. How we do this? As we used to do it in the past, any missing variable puts, for example, if the missing is a plus a bar, put it like this. So I'm going to write it here. This is the missing variable here is d, so a bar, b bar, c bar, and the missing variable is d. Then d plus d bar. Let's go to the next term. Plus the missing variable here is a in the second term. Therefore, it will be a plus a bar times b bar c d bar. Then plus the third term is already 4 variables, so it should be fine. Then the last term, the missing variable is d, so it will be a b bar c bar, then the missing variable d plus d bar. Now let's do the multiplication. So it's going to be a bar b bar c bar d plus a bar b bar c bar d bar. Then let's go to the next term. It will be a b bar c d bar plus a bar b bar c d bar. Just do the multiplication. Then plus the third term, no change on it, a b c d bar. Then plus the third term, do the multiplication, a b bar c bar d plus a b bar c bar d bar. Now let's think, is there any terms are in common? Let's see. Do you think there will be any terms in common? I think there should be 2 terms at least in common. So a b bar c bar d bar, a b bar c bar b bar c bar. Okay, we can think about it like by giving the corresponding value of it. So this is 0 0 0 1 0 0 0 0 1 0 1 0. This is 0 0 1 0 1 1 1 0. This is 1 0 0 0. Here is 1 0. Okay, this is 1 0 0 1. This 1 0 0 0. Okay, so is there any terms are in common? I don't think so. A b bar c bar d. Okay. I think a b bar. Oh, there is a bar here. Then let's find the corresponding values. So 0 0 0 1 is equivalent to, convert this to max term, min terms. Equivalent, this is to 0, and this is equivalent to 1. This is equivalent to 0. 10 10 is equivalent to I think 11. 0 0 0 1 1 0, this is equivalent to 2. This is equivalent 1 1 1 0, equivalent to 15. Oh, 14. Or yes, equivalent to 14. 1, 0, 0, 0. This is equivalent to 10. No, not 10. Let's see. 0, 2 power 0, 2 power 1, 2 power 2, 2 power 3 is equivalent to 8. While this one, I think 10, yes. Okay, so as a result, it will be including minterm 0. I can write M0, 1, 2. After that, we will go to 8, 10, and 14. Okay? Then, let's draw the Carnot map. The Carnot map, according to Carnot map, this term should be CD. This term is AB. So this is the area of C. This is the area of D. This is the area of A. This is the area of B. Then don't forget when you to write on the corner the number of minterms. So here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then, now we are ready to put the minterms. So to put the minterms, there is, which is this our location of ones, the minterms. So there is 1 at 0, 1, 2, then 8, then we have 10, and 14. Where is 14 here? Okay. Now how to group them? We can look at the corners. This corner with this corner, this corner, this corner, they all can be grouped. Because imagine, Carnot map, you can imagine as a sphere. So these corners can meet. Therefore, we can say that we can group these in the corners. Take these corners. How about the remaining element or the remaining ones? We cannot group these three because we need to have 4, a combination of 4s. So we need to have a group 16, 8, 4, 2, 1. So we can group these two together. Then the other one that remains, we can group it this way, like this. So as a result, we have 3. How can we group them? So we can look at the first one as this location located into the D bar area, and look at the variable B. Here is location of variable B. Here is D. So they will be in the opposite area. So it will be B bar, D bar. So it will be B bar, D bar. How about the other elements? Like this one, this one include 3 variables. So these 3 variables, let's look at the variable A. It will be in A bar because this is A, then A bar is the opposite way. Look at the variable B. Here is B, then it will be in B bar area. A bar, B bar. Look at the variable C. This is C, while this area is C bar, so it will be C bar area. So therefore it will be A bar, B bar, C bar. A bar, B bar, C bar. Then the last loop, which is here, the last group. So this is located within, look at the variable A, which is located in A area, within A area. However, in B, this is B bar, therefore we cannot use B. Look at the variable C. Here is C area, so it's within C area, not C bar, so this is C. How about D? Look at the variable D, which is here. This is the area D, this is the area of D bar, therefore it will be in D bar area. So as a result, the minimum of this function, f will be B bar, D bar, plus A, C, D bar, plus A bar, B bar, C bar. This is the minimum function. Yes?
So I have to
Excuse me, which one?
What happened to M9? For the A, B bar, C bar, D. It's to the very right.
Yes, so A, B bar, C bar, D bar.
The one above it.
Above it, yeah. A, B bar, C bar, D. Yes.
Isn't that M9?
M9, oh, I think so. Let me double check. This is 1, 0, 0, 1. Yeah. I think I missed this, right? I didn't write it. You're right. Thank you. Yeah, when I write this, I forget to write the minterm associated with it. So let me write it. So it's going to be M9. That's right. So here is M9. Then in the midterms, there should be 9 with it here. Then we need to include 1 at M9, which is here. You're right. Yes?
I also think you missed a dot on M14. I think that's supposed to be M6 unless I made a mistake.
And the 14th here.
Yeah, I think it's supposed to be A dot.
Here it's A bar, B, C, D bar. Yeah. Okay, let me do it. Thank you. Which is here going to be 0. Okay, I apologize about these mistakes. Okay, it will be A0, 0, 1, 1, 0. So it's going to be 6, not 14. Right? So we have 6, 9. Okay, let me rewrite them. So we have 0, 2, 0, 1, 2, 4. There is no 4. 6, then 8, 9, and 10, right? 1, 2, 3, 4, 5, 6, 7 terms. 1, 2, 3, 4, 5, 6, 7 terms. So let's rewrite this. I think we need to erase everything. Okay, apologize about this. Okay, this is the location of B, location of A. Here's C, D. Okay, now let's write them in terms again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now we're ready to rewrite them in terms to my location. 0, 1, 2, 6, 8, 9, 10. So let's group them. These corners can be grouped. Then what else? We need to group include the other ones. So we can include them by making these two together, or actually we can group it in different way, which is, look at here, we can group this together, include these 4. Okay? Then they add the last one, which will be these 2 together. Okay? Now, let's rewrite it again. This is let's choose the purple one. So these 4 corners, as I mentioned earlier, it will be within the B bar, D bar. Then, for this corner, it will be, or for these 4, it will be within A is not an option. B, it will be within B bar. Look at C, here's C, then it will be within C bar. Then the last one, which is in yellow, it will be within, look at the variable A, it will be in A bar. B is not an option. C, within C, then D bar. So as a result, the function f can be represented as B bar C bar plus B bar D bar plus A bar C D bar. Okay? So we can say that this is the shortest way to represent this function. So instead of using the Boolean algebra equations or Boolean algebra theorems, then we can use this Carnot maps. So the problem will be much easier. Okay, any question? Okay, there's another example here. 0, 1, 2, 3, 4, 5, 7, until 15. So we need to calculate Carnot map or to define the minimum realization. So let's assume that this function, we already convert this to minterms and we need to do our analysis. So here is CD and here is AB. So this is the location of C, this is the location of D, this is the area of A, this is the area of B, okay, the location of B. Then minterms, as I mentioned earlier, we need to put the minterms location in the corner, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay? Now let's put the location of ones. So the location of ones, 0, 1, 2, 3, 4, 5, 7, 14, 15. Okay. Now in this case, let me double check. 0, 1, 2, 3, 4, 5, 7, 14, 15. We cannot group 8s because we have a missing variable here. We cannot group these 8s. So what should we do? Can we group 4s? Yes, we can group these 4. Okay? How about we still have 5 elements left. How can we group them? We can group these 4 as well, right? Now we still have 3 elements left. What should we do? We can group these 2 as well, right? So what else? There is still 1 element left here. What should I do with it? Look for a way that you can group it in the largest number of ones possible. Can we group it in 8s? No. Can we group it in 4? Yes. Then that's it. Group it with 4. Let's color it. We can group it with this. Okay, clear? So it's very important. When you look for the largest number of blocks possible. That's the way, like the largest possible number. So if you can make it 8, do it 8. If you can make it 4, do it 4. Then look for 2 and so on. So how we can group this? Let's look at the one in yellow. In yellow color, it's include 4, so it should include 3 variables. So it's within, look at the variable A. So it will be within A bar. A bar, look at the variable B, sometimes B bar, so B will be the missing variable. Then look at C, it will be in C bar. How about D? I think it should include 2 variables. Okay, I think A bar, C bar, I'm sorry. 4 blocks include 2 variables. How about the blue color? And the blue color, it's located within A bar, because not within A bar. Look at B, sometimes B, sometimes B bar. I'm sorry, sometimes B bar. So it is not within B. Look at C, sometimes sometimes C bar. Here's C bar, then of course not C. Don't use C. Look at the variable D. This is the area of D, then that's fine. So it will be A bar D. Then let's look at the third loop, which is in orange color. In orange, here, look at A. Here it's located in A bar area. So it will be A bar. Look at B. Here is B, and here is B bar, so it will be within B bar area. A bar, B bar. How about C? Sometimes C bar, so of course C is not an option. How about D? Sometimes D bar, so D is not an option. So it will be only A bar, B bar. Then the last one, which is look at the, here's pink color, so includes 2, there should be 3 variables, so it's within A area, then B area, C area. While D, sometimes D bar, so D is not an option. Okay? So it will be A, B, C. A, B, C. So as a result, the function will be A bar, C bar, plus A bar, D, plus A bar, B bar, plus A, B, C. So this is the minimum function that we can achieve to get this. Okay? Any question? Okay. Now in Karnaugh maps, we did the simplification, which is sum of products. We used to do sum of products. That was what we used to do. So which basically based on min terms. Min terms, which is location of ones. Now there is another Karnaugh map simplification using product of sum. In the past, or the previous examples, if we have max terms, we used to convert this to min terms. Now there is another realization or another simplification is to use a product of sum, which is basically we will use max terms. So max terms will give you location of zeros. So in the previous one, in the product of sum, we used to group ones. Then if we need to use the different realization, which is product of sum, we can group zeros instead of grouping ones. This is another representation, which is like by looking at the homework problems that you have, the last problem of the homework, which is using product of sum, which is grouping the zeros. So it will be the same way that we used to do it with Karnaugh maps, but keep in mind we are grouping the zeros, not grouping the 1. This is a different realization. The defaults every time when you use Karnaugh maps is to use the Karnaugh maps that we used to deal with in the past. Unless you see a question mentioned that use product of sum, then you can group the zeros. Otherwise, use the methods that I used to apply in the past. So how we deal with this? The first step, here again, we are dealing with products of sum. I think here there is a typo mistake. It should be product of sum. And dealing with product of sum, so we will group the zeros. At the end, this will be actually f prime or f bar. Then we will do the complement of the final answer to get f, because f bar bar will be f. When you are grouping the 0, you are grouping the complements. That's why we are grouping F bar. After that, you can do the bar, F bar bar to find the final answer. So this is another way to find Carnot maps using product of sum. This is not most likely the common, which is the sum of products, which is the problems that I showed you earlier. But this is just for your information in terms that if we need to figure out how do we do the analysis. So let's look at this example. I'm going to write it in different piece of paper because I don't prefer like this way. They're using different methods. I'm going to write it here. So it is the same as this example. We need to find 0, 1, 2, 5, 8, 9, and 10. So using product of sum, not sum of products, which is we need to use the location of zeros. Location of zeros. By looking at this, all of the given in min terms, they are not max terms. What should we do? Convert the min terms to max terms. So let's convert this to max terms first. So it will be pi as a multiplication, then max terms, the sum of, make the complement, because we know 2 power 4, which is 16, so the range between 0 to 15. So 0 included, 1 is included, 2 is included, 3 is not, 4 is not, 5 is included, 6 is not, 7 is not, 8 is included, 9 included, 10 included, 11 is not, 12 is not, then 13, 14, 15. Okay? Now let's do Carnot maps, the same as usual. Let me draw it. Four rows, 4 columns. 0, 0, 0, 1, 1, 1, 1, 0. Remember, it's like a Greek code. 0, 0, 0, 1, 1, 1, 1, 0. So here is CD, here is AB. This is the area of C. This is for D. This is the area of A. This is the area of B. Then put in the corners the numbers of the min terms, the location of min terms. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, put the location of zeros instead of ones, because location of zeros. Remember, don't put ones. This is because we are dealing with product of sum. Location of zeros will be at 0 at 3, 0 at 4, 0 at 7, 0 at 11, 0 at 12, 0 at 13, 0 at 14, and 15. Okay. Let's look at it. So we have 3, 4. Okay. 3, 4. Okay. That's it. So how can we group these? Remember, we are grouping 4, not grouping. I'm grouping zeros, not grouping ones. So how do we used to group them? Look at the location of them, which is. We can group these 4 together. Then we can group these 4. Right? Is there any elements left? Which is we have the 0 here, that's at 4. Okay, so
Missing the 6.
that's what I'm thinking. I'm missing the 6, right? So we have 0 here. Okay, now I think it has a clear image. Then we can group this. Right? So as a result, we can group each one. Let's look at the orange one. And the orange, it stands for B D bar. B D bar. Then let's look at the purple or the pink. Pink includes CD. And look at the yellow, includes AB. So as a result, we can write F equals to CD, B D bar plus CD plus AB. Remember, this is the location of ones, therefore it's F bar, not F. Okay? Then, how to find F? F equal to F bar bar. Therefore, we need to find, like, we would say B D bar plus CD plus AB. Then they are all bars. Okay? And remember, in De Morgan's theorem, xy bar will be x bar plus y bar. So any multiplication will be multiplication will be multiplication will be addition, any addition will be multiplication. Any one will be 0, any 0 will be 1. So in order how to find the complement of this term, it will be B bar, then there's multiplication will be addition, plus D bar bar will be D, then there is plus, this will make it multiplication, then C bar plus D bar, then there's multiplication, A bar plus B bar. This is F. Okay? Clear? So what's the benefits of this? We will get the final function F as product of sum. They are sum, then products. Right? Okay? Any question? Now, you should know how to do the homework problems in an easy way. The next step is, how about the Gates implementation? How the Gates implementation will be. There is a product of sum, there is a sum of products. So when we do the Carnot maps, let's imagine after doing the Carnot maps using product of sum of products, which is the regular Carnot maps, the function it was like this. B D bar plus B bar C bar plus A bar C bar D. And when we do the product of sum, the function will be like this. Okay? Then how can we deal with this function, or how can we implement the gates or the logic gates? So how, like, I did my own design, convert the problem into variables, then after doing this to variables, make the conditions, create a function. Then the function was not simplified, find the canonical forms, do Carnot maps. So the overall problem will be shorted to get this function. So this is my final results. So in the past, on the previous two lectures about Carnot maps, we used to get the function. Now, how to manipulate the function into logic circuits. So we can build my design. So the logic circuit, when you get this function like B D bar plus B bar C bar plus A bar C bar D bar, we should be aware, we know that each term is basically AND gates. Then we will put them all in OR. So in sum of products, each term is AND gates. Then group them in one OR. Okay? However, product of sum is the opposites. Product of sum, each term is OR gates. Then group them in one AND. Okay? So sum of product, we used to group ones. Product of sum, group zeros, then find F bar bar to find the complements, right? That's what we used to do. So that's how we make the gates implementation. So you should be aware of how to do it. So again, sum of products most likely will be multi and, however, it includes one OR. While for product of sum, it will be multi ORs and include only one AND. Okay? So for example, it will be like AND like this way. Then it will be only one OR. However, this one, it will be ORs. Then they all will be in one AND to get the function. Okay. In summary, we know how to do Karnaugh maps. Karnaugh maps can be divided into two ways. The normal way that we used to do it, which is the sum of products. Basically, we used to group the ones and get the function. Product of sum, you group the zeros. After grouping the zeros, you will get the function f bar. This is not f, this is f bar because we are grouping the zeros. Then find the complement using De Morgan's theorem to get the function. Then it will be as products of sum instead of sum of products. That's how we deal with it. So in case if you see any of this in the exams, you should be aware how to deal with all of these. Let's implement this function as a logic circuits. So here is B bar D, C bar D bar, A bar B bar. How to implement this as a logic function? So what I encourage you is you can have, I'm gonna put it in, I need to have a space like this here. You can make, here is A, here is A bar, here is B, here is B bar, here is C, here is C bar, here is D, here is D bar. Now we have 1, 2, 3. 3 logic gates. There are 3 ORs. Then they will be with AND. So here's the function f. Now, how to connect these 3 ORs? Look at the first term, which is B bar D. Here is B bar, and here is D. The second one, C bar D bar. Here is C bar, here is D bar. The third one, A bar B bar. Here is A bar, here is D bar. Make sure like to put like this to make sure that the intersection is happening here. Then that's how we manipulate the function. So in case if you see this in the quizzes or the exams, not only find the Karnaugh maps, draw the logic circuits, so you should be aware how to do it. This is using product of sum. How about, let me go one step to the previous example to make sure how it will be in sum of product, and let's see how do we manipulate this. Let me give you a few seconds to write, then we'll go there. Okay. So we got this function, which is based on sum of products. That's not the product of sum, which is the normal Karnaugh maps that we use to deal. Which is here is A, here is A bar. This is B, here is B bar. This is C, here is C bar. This is D, here is D bar. You know this triangle with the bubble means this is not operator, which is the bar. Now we have how many terms? 1, 2, 3, 4. 4 terms. So we need to have 4 AND gates because it's products. Then all of these 4 AND gates will be connected with one OR to get the function f. Now, how to connect these 4 AND gates to this? So the first term is A bar C bar. the first term. So A bar, C bar. So done. The next term, A bar, D bar. Here is A bar. I think AD, not A bar, C. Come on. Sorry. A bar, D. A bar, and here is D. The third term, the second term done. A bar, B bar, the third term. Here is A bar. Here is B bar. Then the third, or the last term, the fourth term, A, B, C. Here is A. Here is B. And here is C. Then we are done. That's how we manipulate the function. So, in hardware, we can make this connection to make sure that we can obtain this function. So if this function, for example, for the fan speed control, then you can put it like this way, such that A, B, C, D are the variables which are the measurement of a sensors. So it can be, for example, humidity sensor, temperature sensor. All of these signals will give me some variables or some indications. Then basically, remember like the fan speed example that we already convert this from fan speed or from variables to be as booleans or as from verbal problem to be as variables like A, B, C or X, Y, Z. Then after that, the next step, we convert or manipulate the function f, then convert this function f back to from function complicated one to be simplified using either Karnaugh maps or using canonical forms, or using the Boolean algebra, but we prefer to standardize our answers, so we need to use Karnaugh maps by converting the function to canonical form, then make the simplification to get the simplest way. Then after that, manipulate it using sum of products or product of sum, depending on the function. Any questions about how to manipulate the circuits? Because this will be required for you in the tests as well. Okay. Now there is, I already discussed about product of sum implementation. So, there is a function here. It's called don't care. What does this mean and why this is important? So sometimes, when we do some analysis, we don't care of that sensor measurement if it is on or off. So for example, if we need to make sure that to turn on the fan, we don't care about the light if it is on or off. We need to look at the fan if it's on or off based on the humidity, based on the temperature. So sometimes we have some measurements about the lights and it's already been included into my system. So I don't care about it. If the light is on, turn on the fan. If it's light off, turn off the fan. There's no worries, no problem about it. So these functions or these don't care, sometimes it can be included within my program, within my software, and I don't want this to affect into my program. So I don't want to take the measurements or make the measurements of the lights to affect into the fan. So what should I do? Sometimes we need to make a combination with it. So you will see it into the min terms or the max terms as a don't care function. Sometimes this don't care, we will represent this by X. Sometimes we will represent this by D. So the textbook most likely represents the don't care by D. Here in the notes, it will be represented by don't care. So the don't care means we will use it if we need in Karnaugh maps. How we do the don't care in Karnaugh maps? Let's assume that in 3 variables Karnaugh maps, we have here don't care function, we have here is 1, 1, 1x. How to group this? Most likely, if we don't worry about don't care, if we don't want to use it, we can say we will group these two, this, and we'll group these two, right? But here we can take the advantage of don't care, which means we can use it if we can make this function is more simple. How? If we group this don't care with this one, we can get a combination of 4. Then we can use it. How about this one? Do we need to use it? No, don't use it. Because it's don't care. I don't care about it. So our targets, when we have don't cares functions, we will use them, or don't care terms, we will use them if we can make our loop or our blocks or our selection larger. If we can make it larger, then use it. If not, don't use it, don't care about it, because it's don't care function. Again, in the function, we will remove it, or sometimes we denote it by d, sometimes by x. So in don't care functions, we can make them as ones if we need them. If not, just don't worry about it. Let's look at this function here. Oh, yes. Okay, I don't think I prefer this way. Let me draw it in my solution, my own solution. You will see most likely the don't care functions is given like this way, which is separated than the function itself. So here, this is for the don't care. This is the function. Our target is to manipulate the function, not to manipulate the don't care. But we will use them for simplification if we can. So let me draw the kernel maps. 4 rows, 4 columns. Here is CD, here is AB, gray code 00011110. So here is the location of C, here is the location of D, 00011110. Here is A, here is B, then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So let's put the location of ones first. The location of ones, that's at 1, 3, 7, 11, and 15. Okay? Now let's put the location of don't cares. Don't cares are located at 0, and let me put it as D. The textbook using D. Sometimes D or X, doesn't matter. So D, and location D at 2, then at 5. Okay? Now how can we group this? We can group them. The first step, which is these 4 ones, have been grouped. Okay? The only one that we have this one. How can we group it? If we will not use the don't care, we will group it like by merging these 2, right? This one and this one. But let's use the advantage of don't care. How can we group it using don't care? Can we make it 4? Yes. How?
Does it matter if you go using 2 of the don't cares or using 1 of the don't care? If you get 4 either way.
Just make sure to get 4, so you can use whatever. Yeah, either way. So you can use this one, right? To get 4. Then how about this don't care? Don't use it. We don't worry about it. This is one way. There is another way actually. We can group this, right? Then don't worry about this, don't worry about this. So sometimes when we are using the don't care, we might get different solutions, and both of them are correct. So here, I'm gonna draw it in different colors. So we have, okay, let me make it first the same color here. So this is solution number 1. So we have 2 solutions. So number 1, the first, or by looking at this loop, it will be within the area of, is not E or B, it will be between CD. It will be CD, then let me write it as a function f. F equal to CD, and the other area will be A bar is not within B, not within D, not within C, A bar B. So it will be CD plus A bar B, using solution number 1. Solution number 2, I can use these 4 and use this 4. So solution number 2, the first part, which is this row, it will be the same as CD, but the difference is in this parts here. So we will do which is called A bar. It's located within A bar B bar area. A bar B bar area. Okay? So as a result, yes?
Would it be A bar D for purple? For the first one?
For the first one, it will be A bar. Here is the area of A. So this one will be in A bar area. Let's look at B. Here is B. Here is B bar. So B is not an option. Let's look at C. This is C. This is C bar. So half of it here, half of it here. This is not an option. Look at D. D, this is the area of D. So it's within D. Therefore, it's A bar D. Oh, I wrote it as D. Oh, okay. A bar D. I think sometimes typo. A bar D, right. So we have two solutions. CD plus A bar D or CD plus A bar B. Let me make sure I write it in the right way. And that's both of them are correct. Then that's fine. It doesn't matter. It's don't care function. Okay, any question? So whenever we are dealing with don't care, you can group anyone more like convenient for you. So here is an example. This example is actually written, let's forget about the written words, let's look at how we group them. And because again, when I make my notes, I make it in different way that the textbook have, so now I try to change it to be suitable to the textbook. Now, how we can group this? Again, don't care, you can write it as X, you can write it as D, it doesn't matter. So if we don't want to use the don't care, we can group these two alone, we can group these two alone, these two alone, and these two alone. So this will not be very simple. But if we will need to use the don't care, we can group these 4 alone here, these 4, then we can group these 2 here, we can group these 2 here, then we can group these 4 as well. Okay? That's one way. There is another way, so which is the same as this option. Group these 4, and group these 2. Since we're dealing with don't care, this does not mean this is the only solution. We can obtain different solutions. Like what? We can make sure we can group these 4. Then we can group these 2 and group this alone here. Then after that, we can group these 4. And they are all correct. So again, when we have different answers, so there is option 1, option 2 as shown here, they've already been here. These 2 options, they are both correct. So don't worry about using don't care. Maybe you get different answers than your colleague, and that's fine. Now, how to manipulate function number 1. So this is the area of C, D, here is A, here is B. So by looking at this, it will be within A, B bar. Then this one, it will be within A bar, B, C bar. Then how about this one? It will be within A bar. Sometimes, so B is not an option. C bar, D. So 1, 2, 3, then the last one here, which is plus within C, D bar. This is for function number 1. Function number 2, look at the first loop here, which is A, B bar, or the first option here. The second one, this, which is located with A bar, B, C bar. Then we have this one, which is located at it's not at A. Then let's look at B, within B bar. So C, C bar, D, and the last one, which is C, D bar. Okay, so you need to be aware how to deal with this in short time and fast way as well. Okay, so we have two solutions, and they both are correct. So no worries about it. Don't worry about it. So we can have 2, 3, or multiple solutions, and they are all fine. Okay. This is another example. Again, let's forget about what's written here because this is based on different notation. Here is CD, here is AB. So this is the location of C, this is the location of D. Here is A, here is B. Then the same way here is A, here is D, here is C, here is B. Okay, so we can group this in different ways. So again, like there are many solutions, so we have don't cares, so we can group these 4, then group these 4. So the answer F will be as A bar, C bar, plus, this is the first loop, second loop, D and C. So this is still the same function, but another solution, we can group these 4 and group these 4. That's fine. Make sure just to group to cover all of the ones. You don't worry about covering the don't care. So this function will be including the first one, which is A bar, C bar, plus the second one, which is D, or B bar D. Okay? Any question? So that's all about Karnaugh maps. Now we will go to another topic, still within the scope, like Karnaugh maps, but how do we do this in real life in hardware? Remember, in Karnaugh maps, it can be as sum of products or product of sum, grouping zeros or grouping ones, right? Then the final answer in Karnaugh maps, in sum of product like AND gates, then they will be connected to OR, right? So we have AND, we have OR gates. However, in product of sum, there used to be OR gates, then they will be connected with AND, right? So there will be OR AND gates. Is that right? Let's recall, maybe I think 2 weeks or 3 weeks ago when we discussed about the logic gates, the integrated circuits. Do you remember when I mentioned about the transistors? The logic gates are based on transistors, so how the IC is being integrated, and how about do we make the MOSFETs or the call it CMOS or PMOS or NMOS, these kind of transistors. And remember that I'll show you one I think it's already been in Canvas. I can show you, just recall what I discussed in the past. Files, additional notes about the logic gate. Oh, I think this one, yes. Like MOSFET transistor, and I told you in the real life we have NOR gates, NAND gates, and NOTs. That's all of what we have in real life, right? So how we can manipulate OR gates? We can, or NAND gates, we can put NAND plus NOTs. NOR gates, we can put NOR plus NOTs. So how can we manipulate the Carnot maps that we have here in real life? Here we need to have AND. But our real life, in daily life, we have NAND. So what shall we do? Someone can say, I can put NANDs, put NOTs. NANDs, put NOTs. Then here, I can put OR, then put NOTs. Someone can say like this. This is not actually practical. Why? You are increasing the number of gates. 1, 2, 3, 4, 5, 6. And our target is to use as low as possible. So how can we achieve this? Because we did Carnot maps to reduce the number of gates, to reduce the cost, to reduce the price, or to reduce the energy being consumed, to reduce the complexity of the software or to the program or to the design. So our target is to make it as simple as possible. Then when I go to the real hardware problems, after I did Carnot maps, I realized, when I apply Carnot maps, the problem will be more complicated, or I'm using more gates than what's supposed to be. So do you think this is a good solution? Of course not. Then we need to make an implementation, something that I can convert this. Can I convert it to Carnot maps, or to convert the sum of product or product of sum? Can I convert this to NAND implementation? So basically, we realize that you can convert this to something is called NAND implementation. And you can convert this, something is called NOR, to NOR implementation. So in this case, if I can convert the sum of products to be NAND to NAND implementation, I can guarantee all of the gates that I have are NAND. Then I don't worry to worry about how to make the software will be suitable for it. And when I convert OR to, when I apply this in hardware, when I apply OR and AND to be NOR to NOR implementation, then I will not worry about converting this to be in hardware, how to apply this in hardware. So this thing that we call it as a new topic, NAND and NOR implementation. Basically because, again, the digital logics are constructed based on NAND and NOR gates. So we are not using actually in real hardware problems AND and OR. So we need to make it to convert all of this chips or all of this design as a final stage to be realistic, more realistic. So again, when we do our design, we already have some sensors, have some device to run. Then we need to make sure to build up the problem. When should I run this device? I convert this to a written problem. After that, I can assign variables. The reading of the, for example, temperature sensor is variable A. Of the humidity is variable B. Of the light is variable C. Then the function F is the fan. So I need the fan to be on and off depending on the sensor measurements. So I need to have some conditions. If temperature is high and if the humidity is high, then turn on the fan. If, for example, the light is on or off, this is don't care function. So I can convert this to algebraic equation, Boolean algebraic equation. Then after manipulating this to Boolean algebraic equation, this design is not simple. I need to simplify it because this design includes a lot of variables and maybe a lot of logic gates. I need to make it simple. Convert this to canonical form. After converting this to canonical form, you already have your canonical form. Make it to min terms. Apply Carnot maps so we can get the minimum function, the lowest function possible. Then draw the logic circuit using sum of products. We will get this one. After that, this is not the real one. I need to make sure that it's more realistic problem. So what should I do? Convert this to NAND implementation. After converting this to NAND, then problem done. I can apply this in hardware. I can go to the lab, connect these sensors with these gates, with these logic gates into these integrated circuit gates. Then I can obtain and make my design. Then I can, after making my design, I can sell my product with the lowest number of gates possible, lowest expenses, lowest complexity, lowest energy consumption. Then that's my product is being finalized. So that's the idea. That's why we are learning how to use Karnaugh maps. You need to simplify our design. That's why we are learning how to use Boolean algebra or Boolean stuff like Boolean functions, because we need to implement, convert the verbals commands to be into a function. And that's why we are using and or gates, because we need to make sure how to build our design. Then at the final step, convert our design to NAND gates, or to be more realistic. Then we can make our design, which is called the first half of this course, combinational logic circuit gates, which is basically you can build your own design to make this a specific task. Okay, so our target, how to convert all of these gates to be NAND or NOR. Let's look at the NAND implementation, then we will see how to observe the NOR. So let's take about NAND first. NAND operator, it's depending on how we can convert this function. So we have the inverter. Inverter is already built in. How about to include the NAND based, or to make the AND based on NAND? Not, NAND, okay, let me use a different color. NAND is actually not plus AND, is that right? So this is nuts plus AND. So in order to get AND, we can say NAND plus nuts, we will get AND, right? Therefore, here is the NAND gates that we have in real life. We can add inverter here to get AND. So NAND plus nuts, we will get AND. How about OR? Or we can put the operators into the inputs, not the outputs. Or we can put the nuts at the inputs. So here in NAND, it's actually XY bar, and we'll put bar. Therefore, nuts, I think, let me make sure if it's, we will find the complement for it. Okay, let me erase this. Here in NAND, or in order to create OR, we will put bars above the inputs. So here is X bar, Y bar, then here is X bar, XY bar, bar. Therefore, according to we call it De Morgan's, it will be X plus Y. That's how we get it. Okay? While here, F equals to XY before the AND here, then the function here, XY bar, we will make it F bar to be XY to make the complement over all of the function overall. Then that's how we do the implementation for and OR. So in addition, or in other words, put nuts after the AND, or put nuts before the NAND to get AND. To get AND, put nut after. To get OR, put nuts before at the inputs. So let's imagine that we have this. Okay, let me make it as a sum of products. Sum of products. Okay, I think we are running out of time. Let's continue this next lecture. Okay, we will continue this next lecture. And